Hey guys, let's go and pick up on part 2 of the chemistry chapter 2. So this is the part that we didn't really go into on the last time. Atoms can bond in 3 ways. There's an ionic bond, and an ionic bond, we'll talk more about this in detail coming up in just a second. Ionic bond, we take an electron, it completely leaves one atom and goes to the other. The other way that they can bond is by sharing an electron. Now, they can share that electron in one of 2 ways. If you look right here, you can see that there's water and then there's carbon dioxide. Now, oxygen is a little bit electron hungry, so it tends to pull the electrons closer to it. By pulling the electrons a little bit closer, they have a partial negative charge. That's what that little squiggly line that right there is indicating. By having the electrons a little bit further away than as if they were sharing equally, those hydrogens are a little bit more positive than neutral. And then you have the nonpolar covalent bonds like carbon dioxide. Oxygen does tend to pull, but in that case you have oxygen on 2 sides and they're pulling against each other, so they cancel out. We'll talk a little bit more about this in a little bit detail. Okay, as far as the ionic bonding, these guys, something like sodium chloride, that's just table salt. What happens, and remember we were talking about the periodic table, that I said sodium had 1 electron in that outer shell. Now, it needs to get to 8 to fulfill the octet rule, but sodium has got to get 7 electrons to be filled. It would be easier for sodium to lose 1, and I don't mean share, I mean lose. So sodium wants to get rid of that one and make itself stable. Chlorine, on the other side of the periodic table, has 7 electrons in its outer shell. It needs 1 desperately, and it's going to take 1. So sodium and chloride is a marriage made in heaven. Sodium wants to get rid of 1, chlorine wants to take 1. So that actually, we have an electron leaving the sodium atom and going and becoming part of the chlorine atom. Now, remember we said that we had the equal numbers of protons and electrons. So if I have I'll make up a number, +8 and -8, it's neutral. It balances. It's totally they cancel each other out. But now let's think about sodium. Can't remember the atomic number. I'll make up one. No, I don't have to. I can count. 8, 10. It is 11. So sodium has an atomic number of 11. That means that when sodium loses an electron, it has 11 protons and 10 electrons. So all of a sudden I've got 11 pluses and 10 minuses. So I'm going to wind up with an extra positive charge. So sodium actually has a positive charge. Because of losing that electron, it now is positive. Now I don't remember chlorine's atomic number, but the fact of the matter is chlorine had an equal number of electrons and protons, but then it got a new electron, and now it's got 1 more electron than it has protons. So again, I'll make up a number. Let's say it's 15. It had 15 protons, now it's got 16 electrons, so it's going to have 1 extra negative charge. So it's going to have a negative charge. If you look right here, we have names for these guys. Anions are a negatively charged atom. These guys are called ions. That's why they're called ionic bonds, right? The positive charge has the name of cations. Now, this is where the bond comes in. All of a sudden, sodium is positive, chlorine is negative. Opposite charges attract each other. Now, it's not a real strong bond, and these guys basically, break apart in water, but it is a bond. And it's strong enough to make salt crystals that we put on our french fries, right? I don't know if you guys can see that. That looks awfully small. But anyway, there you see it right there. There's sodium losing that one. And again, now this guy has 11 protons and 10 electrons. So he's going to have a +1 charge. But for sodium, he's got 8 in his outer shell, so he's stable. Chlorine, let's see, I could probably calculate that. 2, that's 10. Its atomic number is 17. Oh, I could have looked right there. So 17, when he gets the extra electron, he's going to have 18 electrons and 17 protons, and he's going to have a negative charge, a charge of -1. So these negative and positive charges are attracted, and they actually attract like this. The green ones are the chlorine, it's a little bit bigger atom, and the smaller ones are the sodium. They're attracted to each other, and so the negatives and positives line up, and they actually form like a matrix, a lattice, and that's the salt crystals. Okay, covalent bonding. They're going to share electrons. Now, it can be as simple as 2 electrons, or it can be a larger number. When you get 2 hydrogens, which each have 1 electron, when they come together and they share it, then they have 2. Remember, the very first shell is stable with 2. But then, they could share more. And even other atoms can share 2 electrons, and that's all they need. Carbon monoxide. Well, no, that's not a good example. But anyway, so we've already talked about how the carbon dioxide with the oxygens on 180 degrees away from each other, their pull is going to neutralize out. If you pull equally in these 2 directions, what's going to happen? Nothing. The forces cancel out. Now with the water molecule, the oxygen is right here, and these guys actually are at an angle, so the oxygen is able to pull those electrons a little closer to itself. Here is some terminology, guys. Electronegative. Now, why does oxygen pull it away from the hydrogen? Well, negative and positive are attracted to each other, right? An electron is negative and a proton is positive. Oxygen has 6 protons. Oxygen has 8 protons and hydrogen has 1. So if you have 8 pluses pulling this electron and you have 1 plus pulling it the other way, it's going to be closer to that. Now, it's not an ion. They don't transfer totally. It's just that they're partially. Electropositive, this is a guy that's going to have a tendency to lose an electron like sodium. If you've got 1 or 2 electrons in your outer shell, it is easier to just get rid of those than it is to come up with 6 or 7 other electrons. So the electronegative electrons, that's going to be like oxygen or like chlorine. Chlorine is electronegative. It's going to want to pull an electron away from another atom because it is so close to being stable that it's highly reactive. That's why chlorine is, like I was telling you guys, it was the basis of the first poison gas that the folks developed. Okay, continuing on. Covalent bonding. Right there you see a carbon. Carbon has 6 electrons, 2 in the first shell, which has nothing to do with anything. They're out of the picture. And then they have 4 there. So carbon needs 4. Carbon is really neither electronegative or electropositive. They're in the middle. And that's also why carbon is a semiconductor, because, well, we won't go there. That's more of electrical than this. But so you see those 4 hydrogen atoms with 1 electron. Carbon will share a pair with 1 hydrogen, share another pair with 1, and so each of those hydrogens sees itself as having 2 electrons, while the carbon sees itself as having 8, and so everybody is stable and balanced and happy. Now, carbon, even though it has more protons than the hydrogens, this is a nonpolar bond, and it has to do with the fact that the carbon is pulling all of these guys basically in opposite directions. It's not a thing. It's actually what they call a tetrahedron, but you guys don't need to know that, so don't sweat it. CH4 is methane. That's one of the most simplest carbon atoms. Oops. Okay, guys. Okay, covalent bonds. Here's 2 oxygen. And we already said the oxygen that we breathe in, the atmospheric oxygen, is oxygen molecule, is a molecular. Now, oxygen has 6 electrons in its outer shell. It needs 2. That's why it gets 2 hydrogens to make water. So what's going to happen is these oxygen atoms are going to share 2 pair of electrons. So this guy's going to have 2, and he's going to have 2, and they're going to make 2 separate bonds, or not separate, but 2 bonds. If you look right there, let me go back just real quick. The structural formula, if you notice that there's the C for the carbon, there's the H's for the hydrogen, there's 1 line. That means that 1 line means 1 pair of electrons. Now let's go back here. These guys, since they share 2 pairs, there's 2 lines. That's called a double bond. So that's the way oxygen exists in the atmosphere, and that's the way we take it into our bodies. I mean, we break it apart, but that's the way it comes. Nitrogen, which is like 78% of our atmosphere, has 5 electrons in its outer shell, so it needs 3. So these guys have to share 3 pairs to be molecular nitrogen, and you can see there, triple bond, you see 3 lines there, and that's all it means. It's a triple bond. Okay. Polar covalent, this is a close-up. So those 4 electrons there were always belonging to the oxygen. They just belong to it. Here is where these 2 right there are the oxygens. Those 2 are the hydrogens. And like I say, since this guy has more pulling power, he's going to pull these things further from the hydrogen and closer to the oxygen nucleus, which is what we're talking about right here. So this is weakly negative, partial negative. It's not a -1 like an anion, but it's a partial negative charge and a partial positive. And that fact is going to be really important for the stuff we're going to be doing coming up. So make sure you understand that. Okay, hydrogen covalent. Now, hydrogen bonds, these are a very weak type of bond. but they're so important. That's why water sticks together. That's why water will bead up on something. That's why those little insects can walk on the surface of the water, because there's such thing as hydrogen bonding, where this guy, remember, he is weakly positive and this guy's weakly negative. They're attracted to each other. And so the water molecules kind of have a weak attraction for each other. This is also what is going to cause your DNA to twist. So it is kind of important, even though it is the weakest of all the bonds. Hydrogen bonding, it's the partial charges that are being attracted to other opposite charges. Chemical reaction, this is where two atoms react. How does this happen? Honestly, the two atoms that have energy, they're moving, they slam into each other, and that's how the bonds form. Now, when chlorine and sodium slam into each other, they come out of it sodium minus 1 electron, chlorine plus. When, say, two oxygen hit each other, they stay together like this. They just share the two electrons, pairs. Any kind of reaction is just when something changes. We either make bonds, we break bonds, or we change the bonds. And I'll show you this. This is coming up as well. So when we do a formula, this is what we do. So there's the reactants. That's what you start with. The product is what you end up with. These two hydrogen atoms, you know, maybe their temperature is high, and when it gets higher temperatures, there's more energy. These guys slam into each other, and they form molecular hydrogen, H2. Methane, the same thing. 4 hydrogens and the 1 carbon are the reactants. And usually you'll see an arrow. Now sometimes we have an arrow that goes in both directions, and that means that this is reversible. Sometimes it's not, but sometimes it is. Well, here's something you need to know, guys. Synthesis just means you combine two things. You take one atom and another atom and you make one molecule. These guys are together. Decomposition is basically what you would think. It's the opposite of synthesis. You've got a molecule and it breaks. If you put electricity through water, you can break the bonds between the hydrogen and the oxygen, and you can actually separate the hydrogen gas and the oxygen gas. Now, the exchange reaction, sometimes one atom will make another atom more stable than, say, his first partner. So there's these guys. We had a synthesis reaction. We have these two atoms together, but it happens that C will make A even more stable than B would. So what happens? This guy throws over B and grabs C. So John takes Mary to the prom, he meets Betty, and goodbye, Mary. He goes home with Betty. Okay. Synthesis reaction, you can see there. Now, of course, this is going to be the anabolic. We talked a little bit about that in chapter 1. This is always forming a bond. So there's molecular hydrogen, 2 hydrogens. There's 2 hydrogens, and there's 2 oxygens. 2H2 plus O2 equals 2H2O. Now, if you take that 2 and multiply it by that 2, that means you have 4 hydrogens. This means you have 2 oxygens. When you end up on the other side, you have 2 times 2, which is 4 hydrogens. 2 times 1, you don't put the 1 down there, means you have 2 oxygen. In other words, the equation is balanced. You always got to have the same number of atoms on the other side that you started with. That's kind of, relatively simple idea. Decomposition, this is like hydrogen peroxide. They put that in a brown bottle to keep the light away from it because sunlight will help it break apart. Hydrogen peroxide is H2O2. That is totally unstable. So when given the chance, this guy is going to decompose. So I've got 4 hydrogen and 4 oxygen. So I'm going to wind up, this is going to decompose into 2 molecules of water. 2 H's times 2 is 4. 2 O's times 1 is 2. And 2 O's over here. So I had 4 oxygen total there, and I've got 4 oxygen total there. But anyway, that's a decomposition. Breaking bonds, that's catabolic. Generally, breaking bonds releases energy. Making bonds requires energy. You've got to have some sort of energy. Remember I told you these guys slam together. A lot of times in chemistry, they'll heat stuff up because that heat energy is going to get these guys going faster. The faster you go, the more chance you have of running into something, right? And so it takes energy to make bonds, and it releases energy when you break them. We'll get into way more about that coming up. And then the displacement reaction, just exchange. So as soon as we get our blood sugar, glucose, into our cells, we take one of our ATPs, and there's a phosphate group there. We attach it to that glucose. Why do we do that? Well, it's going to be used in the when we actually turn this into energy, but it also, phosphate groups are charged, and since it's charged, it's going to keep this guy from floating out of the cell. So exchange reaction, displacement, you both make bonds and break bonds. So we break the bond between A and B, and then we make a bond between A and C. Redox reactions. These guys are always paired, and we'll see why. So here's a guy, he's got 2 electrons. Here's a guy who doesn't have any showing. He's got some, but they don't show. So this guy comes and he gives up those 2 electrons. This isn't the ionic thing, guys. When he does that, he has to give it to somebody, so he gives it to this guy. That's why these guys are always paired. The guy that gets the electron is reduced. The guy that gives up the electrons is oxidized. That's what redox. Reduction, oxidation. We use this a lot in our energy production, so you really need to get a handle on this. It's pretty simple. I mean, I can't just give up electrons. I have to give it to something. So these are always paired. And I think the mnemonic is oil rig. Oxidation is loss. Reduction is gain. I always thought that the guy that got the negative is reduced. You know, if I have a new bill every month, it's going to reduce my disposable income. So whichever one you like, whichever one helps you to grasp this, you really need this. Okay, I've got to move my picture. Exergonic versus endergonic. So this is just definition. There we go. That's just definitions, guys. It's not a real difficult concept. Exergonic means that you release energy, and exergonic is catabolic. Remember, we got to break a bond to release energy. Endergonic means we have to put energy into it, and that's going to be an anabolic because we're making a bond. It's not that hard. Oh, we going to move me again. Chemical reactions, equilibrium. Remember I told you about those arrows pointing both ways? You can see them now. Here's N2O4, and this guy is going to break up into 2NO2, nitric oxide. All chemical reactions are theoretically reversible. Inside of a biological system like ourselves, they're basically irreversible because it takes a lot of energy to reverse it, and when we do a chemical reaction, the stuff doesn't stay in the same place, it moves away. So if it's in the same place, it could go backwards and forwards. Here's what it is, guys. There is a balance point for this. Now, it doesn't have to be 50-50. It could be 80-20. But there is a point where this guy, about 80% of them maybe are going this way to breaking, but 20% of them are coming back the other way. It just depends on the actual substance or the molecule as to which way it is. But that's all chemical equilibrium is. That if you leave the stuff in the same place and a certain number of it is going to go backwards. We do have that inside of us, and we use it for a specific purpose. That's really going to be more of an AMP2 thing, but I think we touch on it. Okay. What makes a reaction go faster and what slows it down? Well, the hotter it is, the more heat energy, the faster they go, the more they bump into each other. So if you increase the temperature, you speed up the reaction. If you decrease the temperature, you slow it down. Particle size. How big are the atoms? Something that's smaller can move faster than something that's big and bulky. So the smaller the particles, the faster they're going to fly and the faster they're going to react. The bigger the particles, the slower, the smaller, the faster. Think about it this way. If you had a little sports car and an 18-wheeler, who's going to win in a sprint? I mean, if they're going 0 to 60, the sports car is going to do it because he has a lot less mass. Even though the other guy has a bigger engine, it's not going to work. The other thing that has is how much if you have of this stuff. So even if I'm driving really fast and I'm in a sports car, my chance of having an accident is going to be greater when there's a bunch of cars around me than if I'm all by myself. So if I go through Jasper on Sunday morning at 6 o'clock, there may be a few cars out, but there's not going to be a lot. If I go to downtown Atlanta about any time or on the interstates, I have more chances. So not only is it going to depend on how fast these guys are going and how small they are, because it makes them go faster, but how many. If I'm going to have a collision, the more of these atoms I have, the bigger my chance. Does that make sense to you guys? I mean, it does to me. Pressure, the increase in pressure, when you increase the pressure, you just actually kind of push the atoms closer together. Again, if you're closer together, if you're tailgating somebody, you're going to have a much better chance of having an accident. Now, there is something called a catalyst. Enzymes are the catalyst that we use. They speed up a reaction, but they themselves really aren't involved in it. It's like the two atoms come and bind to this one molecule, and it just kind of helps them to get together. We could not live without our enzymes. They're mostly proteins, but there's some metals and other things, vitamins. These are the guys that speed up our body chemistry. Without them, and we could still do our body chemistry, but it takes thousands of years for reactions to occur, and that's not fast enough to keep us alive. Okay. here's showing there's two atoms or molecules. These guys fit, and it's like a key in a lock. The enzyme is just a molecule. These two molecules fit in it, and it brings them together in a manner that allows them to bond. So without the enzyme, you need all this energy to get these guys, but with the enzyme, you need much less energy, and it's a lot faster. There's that methane. These guys are equally spaced, and we're not going to go too much into that. That's what the methane, that's C6H12O6. I don't know if you guys can see, but this guy forms like a six-sided circle ring. That's glucose. That's blood sugar. There's the water. There's the carbon dioxide. A little bit bent, but not much. There's hydrochloric acid. This is an ionic bond. You put these guys in water and they're going to separate. Okay, the whole thing on this guy is the difference between organic and inorganic compounds. Methane is organic because it has carbon and hydrogen. This guy's got carbon and hydrogen. It's got oxygen, but that's not important. It's got carbon and hydrogen. These guys, that's water, it has hydrogen but no carbon. That is not organic. This has hydrogen but no carbon, not organic. This guy's got carbon and oxygen but no hydrogen. So that's your definition for organic, carbon and hydrogen. Okay, the human body, 90s, I can't remember what the exact number is, probably in here, but the overwhelming majority of our body, I think it's like 94-95%, is only made up of 4 elements: oxygen, carbon, hydrogen, and nitrogen. Now the oxygen and the hydrogen is mostly in the form of water. You know, we're just bags of water with some other things. But over here you can see how much. Calcium 1.5, phosphorus, potassium less than 1%, sulfur, sodium 0.2, chlorine, it's got to be the same because they came in together as salt, magnesium, and then we got all these trace elements. Some of these you may be surprised. Chromium, wow, chrome plated, copper, iodine, iron, oh, we need iron, manganese, molybdenum, selenium, silicon, tin, vanadium, that's what they coat tools with, zinc. Wow, that's kind of interesting. But we need all of those, and we're not going to actually get into all of that detail. That's not really for our level. Water. Let's talk about water. Ooh. Let me finish talking about water. Let me see. Hold on a minute, guys. See how many slides the water goes. I don't want to start something. Oh, that's okay. Yeah, it's just 2 slides. Let me finish these 2 slides and we'll call it. We're at about the 31-minute mark right now. We already talked about this. 60 to 80% of our cells are water. Outside the cells, most of it is water. We have to have water because water breaks apart ionic compounds like sodium chloride. Sodium is involved in our heartbeat, our muscles moving, and our nervous system functioning. So it's very important that we have water. Now here's some properties of water, and I want you to listen because people confuse these 2 properties. The high heat capacity. This guy will absorb heat or release heat with no temperature change, very little, this guy is going to keep your temperature from running up. Here's the thing, guys. You can sit and watch water boil, and it takes forever. You turn the stove high, and it's still, and there's no bubbling. You don't see very much in the way of steam, and the temperature does not change until it hits 100 degrees C or 212 F, and then it goes up. Let me say this on the other way. You put an ice cube in your soft drink or whatever, until that ice cube is completely melted, the temperature of your drink will stay 32 degrees F or 0 C. That's the high heat capacity. Water has the ability to absorb and get rid of heat with very little temperature change. And if you think about it, we are made up of so much water that if this wasn't the case, then our temperatures would really swing widely, and our enzymes couldn't take that. We wouldn't be able to sustain life. Okay, so that's the heat capacity, absorbing and releasing heat with very little change in temperature. Now, the high heat of vaporization, it takes a lot of heat to change water from a liquid to a gas. Now, whether we're talking about the boiling water, but the way we use this is if it's really hot, we sweat. Water beads up on our skin if the humidity is high. And when that water evaporates, it sucks heat out of our body to do it. That's how we get rid of excess heat. We sweat. If we don't sweat, we've got problems. So the high heat capacity has to do with maintaining the temperature. High heat of vaporization is helping us to dump heat when we're in danger of overheating. Okay, guys. Polar solvent properties. Water is called the universal solvent. In other words, more things will dissolve in water than anything else. So there's our salt, and as soon as it gets in water, that sodium is positively charged, so that sodium is going to separate from the chlorine, and those oxygens, which have a partial negative charge, are going to surround those sodium. If you can look right there, you see those red oxygens. On the other hand, the chlorine has got a negative charge, so the partial positive from those hydrogens, the blue ones, are going to surround it. That's why the ocean's got salt dissolved in it. If you take a salt, put it in a glass of water and stir it up, it will dissolve. This is going to be it's going to be a real important thing that we're going to use the water in our body to break ionic compounds up. Water is the basis of our blood, and as well as the fluid in the cell and outside the cell. I think, guys, that's... Oh, no, I still got another one. I want to finish the water properties then we'll call it. Reactivity. This has to do with hydrolysis and dehydration synthesis. I'll tell you about that. Water is important for breaking things apart and putting things together. Finally, we use water as cushioning. Water, there's fluid around the brain that I don't know if you guys know that whales weigh so much that they can't live, but they beach themselves. Their own weight will crush them. But when you're in the water kind of neutralizes your weight, buoyancy. The same way our brain is kind of fragile and it kind of floats in the water, but it also kind of acts as a cushion to try to slow down, to keep you from damaging your brain by hitting the inside of your skull like in an automobile accident. I'm going to stop right here. I'll talk to you guys about this. I've already talked to you guys about a lot. We'll do this in part 3. All right, guys, thanks. I'll see you.